Hi, and welcome to our new session here in our chapter on risk minimization. So this is on regression losses, so on the well-known L2 and L1 loss. So I will define these two loss functions, and then we'll pretty much talk about or derive their risk minimizers, optimal predictions in an unconditional and a conditional sense. Okay, let's directly start. There's the L2 loss. Very sure you've seen this before. So this measures the difference between a regression prediction, f of x, and a ground truth real valued label y by squaring the difference. And this difference we'll call residual, just a name for the difference between y and f, so y minus f. That's our residual. And we can do it like this here, or you can put it times 0.5 in front of it, then that really doesn't make a difference in terms of where the minimizer is located. We just usually do this because often later on we'll want to look at derivatives, and then it's very nice that the I don't know 2, which goes in front of the thing when we take the derivative, cancels out with a 0.5, but for us this really doesn't matter here. So what is the I don't know effect of using such a loss function? This loss function obviously tries to reduce large residuals quite a lot. Maybe we should actually look at the visualization first. So this is not very difficult. So here I'm just going to put the residual on the x-axis. I'm going to put the loss, the L, on the y-axis. And now I'm just going to plot things. And as you can see, this is a quadratic function. So not that much more to say about this. You have seen the shape before. And here on the left-hand side, I've constructed some simple toy data set. I've apparently fitted a linear model to that, and we can now talk about what a residual is. So residual would be, so here if I look at this point, and I look at the y-axis, its associated y coordinate, that's my ground truth label here, and I can look at the predicted value here on this line, and I can now compute the residual, which is this distance here. And for some weird reason, apparently, I'm now squaring that, and that's my loss value. The reason why I'm squaring that is that makes my loss differentiable. Well, first of all, it gets rid of the sign of the residual. So usually I might not care that much. Sometimes I do, but maybe I don't care about whether I'm underestimating or overestimating things. So I want to get rid of the sign. So the square does that. I guess the other option is what we're going to study here as well, and that's now computing the absolute distance between y and f, so the L1 loss, so to speak. But here we're squaring things, and that makes the loss functionally nicely differentiable and is also convex. And that, the reason why we're doing that, and we'll study this more later on, is it usually keeps the optimization problem somewhat simple. At least it doesn't make it more complicated. It can already be complicated if our f of x is usually non-linear and complicated, some deep neural network, but using now maybe a non-differentiable, non-convex loss function might make things even harder. Also might make it harder if f is not so complicated, and then we might enjoy this simplicity and don't want to destroy it. So things like convexity and loss functions being differentiable, so usually this is nice to us and therefore of interest to us in order to efficiently numerically solve the ERM problem. There are also other connections we can exploit. So there's a deep connection, a certain equivalency between using squared loss and the assumption of Gaussian errors, which I will also explicitly study here in this chapter, but not in this session. Okay, so how about we now consider what are these optimal prediction values I've introduced in the first session here on concerning risk minimization basics. So how would we just compute that now for this loss function? That would be a nice exercise to understand these concepts a little bit better and also to get some concrete results here for this loss function. That would be nice. So, and I want to do this in a very general way for now. So I want to now, I've talked about that, introduced that already in the risk minimization basics session. So I want to now derive a result for an arbitrary random variable. And yeah, I want to consider this, I don't know, M estimation problem here. So I want to minimize the expected loss when I compare my random variable z and some constant c. So let's just plug in our loss function. So now it looks like this. And now the next step is I'm going to expand the square like this. I guess that should be obvious how this looks like, right? This is just the binomial formula. And now because my expectation is a linear operator, I can drive that kind of to the inside of things, and I have this result here. And this result now is very, very easy to optimize because I'm the expectation of z and the expectation of z squared. These are just now constant numbers, right? I guess it's confusing because I'm talking about different constants now, but these are like fixed numbers. We're not minimizing over that, we're minimizing over c, all right? And first of all, this first term here doesn't even have a c in it. So in terms of minimization, I can completely disregard this. So I can just look at these later two guys. And it's pretty obvious what the minimizer of this is. I guess if you really want to compute this yourselves, I don't know, take the derivative with respect to z, add it to c, set it to 0 and solve, or a little formula how to compute the minimizing location for a parabolic function, for a simple univariate quadratic function, because that is what we actually have here, and it should be very, very easy for you to derive that the optimal c value is the expectation of z. Okay, yeah, so now you can also plug it in the formula above, and then you could even compute the associated expected risk for this. Okay, nice. So we now know that this thing here, this is always minimized by the expectation of z. This is the best constant. And I guess you might have heard before that, yeah, the solution of this L2 loss minimization problem is the mean, is the expectation. And that's what we're saying here. But then I'm just going to pointing the finger to the fact that this holds true given any distribution Q. Okay, so as long as we can compute these expectations, I'm not always going to make that explicit here on the slides. And this is a very basic fact. It wasn't very hard to derive, but we can now exploit that in very many different ways, which are actually not that different. So first of all, we could, for example, now say, hey, maybe our distribution that we're considering here is our label distribution. So now we can get our hands on the optimal theoretical constant. So what's the optimal constant prediction model, which doesn't act on any feature vectors? I've introduced this before, right, in the first session in this chapter. So that's this F star C constant predictor, optimal loss optimally constant predictor in a theoretical sense. And I know what that is, right? It's the expectation of y, because it solves this minimization problem here. Yeah, and now my random variable is just called y instead of z, yeah, and it has this label distribution here, so it's just the solution is the expectation of y. So that's nice. So we now know how our optimal theoretical model looks like. And now I maybe want to know what the optimal empirical constant is. So this f hat c, and for that I would have to solve this empirical minimization problem just for a constant. And I guess you already know where this is going, right? It's probably going to be the average, right? It's going to be the empirical mean. And that's certainly true. Thing is, we do want to prove this here. So there are two ways of going about this. We can just like directly consider this problem here and then solve this minimization problem over C empirically. And that's super easy. And do this as a little exercise. Again, yeah, like write this out, plug in the loss function, compute the derivative with respect to C, set things to 0, solve for C, and you will see that you get your hands on the empirical average. But here we can get our result nearly for free from our previous considerations, because considering empirical data is pretty much just considering a certain distribution. So the empirical distribution, and the empirical distribution is this thing here. So this is this average over delta distributions, pointwise distributions, where I have one-point distributions where I'm putting 100% probability mass on the location yi and 0 everywhere else, and I'm now just like mixing them together and averaging them. Okay, so if I do that in such a manner, I have my empirical distribution for such a vector of observed values, and here, I don't know my observed values, I'm just going to call them labels. And now if I want to talk about this optimal empirical constant, I have to solve this minimization problem, but solving this empirical minimization problem is going to be the same as solving this theoretical minimization problem here, and I'm also now plugging in L2 loss, and I know what the solution of that is. It's the expected value of z, and now I know the distribution of z. It's the empirical distribution, and for the empirical distribution, I know how I can compute an expectation, and that's just this here, and that is y bar, which is just an abbreviation for the average. So, okay, it looks a little longer. I'm not even sure whether this is much shorter in writing than directly minimizing this thing here. But yeah, I mentally had to do nothing. Just had to compute the expectation, and that was easy for us to do for this empirical distribution. Like I said before, constant models are interesting as baselines, but we are more interested in optimal point-wise conditional predictions, right? So let's now minimize the true risk for our unrestricted hypothesis space and L2 loss. So we are at some point x equals x tilde, so x is going to be a random variable, and x tilde is like a concrete, I don't know, vector we are plugging into x, and that we want a condition on x being equal to x tilde, and we want to talk about what our loss optimal prediction is. And in a previous session, we derived that our point-wise loss optimal prediction is going to be constructed for a risk minimizer like this, that it's solving this minimization problem. But now this looks very, very familiar to us, right? So this is like this M estimator type of thing. Yeah? So it's a minimizing an expected loss between a random variable and a constant value. And the only difference now is that the distribution of y is not like some, I don't know, unconditional distribution. It's a conditional distribution. It's a conditional distribution of when x equals x tilde. But that's a distribution too, right? Just because it's conditional, it doesn't complicate things a lot. So we can now simply use our results for the true loss. And the nice thing is that this derivation here that I did on this slide, I don't know, require anything about my distribution Q. So it can be also a conditional distribution. So I know the solution. So again, the solution is going to be the expectation of my random variable. Well, it's now a conditional expectation now. That's it. So we know point-wise how our risk minimizer looks like. It's the conditionalist. At every point x equals x tilde, under L2 loss, the risk minimizer prediction, the base optimal prediction, is the conditional expectation of y given x. Yeah, that's it. So under L2 loss, the conditional expectation is the risk minimizer. It's the base optimal model. It's a nice result. Pretty nicely tells us, pretty concretely tells us, given that we know our underlying distribution, that we have access to this, how our optimal predictive model looks like. Pretty much concrete form. That's very nice. Here's another different way of looking at things. It's actually even easier to figure out. So let's just reconsider what we did before. So we optimized for a certain constant, I don't know, conditional, unconditional, who cares, whose square distance to all points in a certain set, so just specifying this here, defining this here empirically, can do this theoretically with the same result, is minimal. So optimizing for a value whose square distance to points in a set is minimal on average in sum. Doesn't matter. And our result was, hey, it's the average. theoretically the expectation. And like I said, let's doing this empirically now here on this slide. So I can just ask myself now, okay, if I take that optimal thing, the y bar, the average of my vector, what's the associated risk? Well, we are still using L2 loss, right? So this here is now my risk. It's the sum over all of the squared distances between my constant y bar, which I'm using for prediction, and my observed ground truth labels. So I'm summing all of this up now. Yeah? So it's the sum of all of these squared residuals. And yeah, why not maybe average them? Yeah? Just for good measure. So I can divide this by n or n minus 1, doesn't matter for now. And because that gives me some version of the variance, like the unscaled or a scaled version, biased or unbiased version of the variance. Don't want to go into this now. Let's just do divide by n. Yeah? And that gives us this, this version of the variance. Yeah? So this is obviously pretty trivial, to figure this out. Pretty trivial, but let's just consider that for a moment. That means if we do L2 loss minimization, we could have also said I'm doing variance minimization, right? And this is very often also what happens in certain books, certain papers, that they talk about variance minimization for models. Yeah, and that's pretty much equivalent to L2 loss minimization, in a machine learning sense. So, and the same principle holds true now for theoretical construction. Yeah, we would then talk about the theoretical variance and the expectation instead of the average. And also holds true for the conditional case, where I'm doing, I don't know, point-wise, conditionally optimal predictions. So what this basically means is that you could explain now variance in very much in a predictive sense. So let's say we have some real line here and I have some data points here, right? And maybe, I don't know, maybe my data points shouldn't be symmetrically distributed around 0, so let's put them here. And I could now ask myself, okay, I have this data here, and what I want to do is I want to specify now, give a different definition, different derivation of what variance is, right? I could ask myself, we have this data cloud here, univariate data without features. So I want to now predict this data with a constant value. I want to have a constant that represents this vector of things, this vector of values. So what's the best value to represent these guys? And your answer should actually not, from now on, be, that's an undefined question, I can't answer that. But if you give me a loss function, I might be able to answer it. So my loss function is going to be L2 loss. So what's the best loss minimal way of representing this vector under L2 loss? And then you're going to say, well, then if I know it's L2 loss, then it's certainly going to be the mean. It's going to be the average. And the next thing we could ask is, okay, what's the associated prediction error on average that we are making? And that is this thing here, divided by n, because I said average error in prediction. And that's variance. So you can say variance, that's the prediction error you're making, and you're representing a vector of numbers by the best optimal constant prediction under L2 loss, which is the mean, and then you're just calculating the prediction error again under L2 loss, and that's variance. And that's I would say, very accessible and intuitive definition of variance, by not, I don't know, going over these other formulas where you compute squares and products and so on. Yeah. So, and these two things are provably equivalent, which might also be a nice little homework exercise for you. I have 2 slides left on L1 loss. Yeah, here's the definition of L1. We again compute residuals, or we consider residuals. And I'm now not squaring them. I'm taking the absolute value of things. So if I plot that, it doesn't look like a quadratic function, because it isn't a quadratic function. It looks like this, I don't know, V thing, which is the usual plot of the absolute value function. And this associated loss is called L1, because of L1 and L2 norms. So later on, we are going to talk a little bit more about that. This is actually what we would call a robust loss function. It's way more robust than the L2. And robust here means that if I have outliers in Y, I mean, I mentioned this before, so L2 likes to really drive down super large residuals. So if I have outliers in Y in my data set, L2 loss minimization is going to really trying to take care of these outliers, which is usually what we don't want, because we don't want to like focus our estimation to on these usually erroneous outliers. So L1 loss is much less sensitive to this because the loss here is not going to go up, I don't know, quadratically and going to shoot up like this, but it's only going to go up linearly, and this makes the thing more robust. And I'm going to show examples later on, so you don't want to go too much into this here now. Again, we can consider the analytic properties of the L1 loss function. It's pretty obviously non-differentiable, so that will make optimization harder. Optimization is not really a focus of this lecture here, although I have a different one where I talk about optimization principles in machine learning, where we would heavily discuss things like that. But here I just want to mention this is differentiable, so maybe things like gradient descent are not going to work that well anymore. Maybe we have to use like derivative-free optimization procedures. The loss function at the very least is still convex, so depending on how our hypothesis space looks like, the underlying risk minimization problem, the RM problem, might still be convex in our parameter vector theta, and that is not completely bad then. Okay. Hi, and as you can see, I now look slightly different. We actually ran into some audio problems when I shot the first video, and I was too lazy to redo everything from scratch. So here we are. So let's just go on and ignore this. Okay, so again, as before, we can now talk about what are actually the optimal predictions under L1 loss. So you can now show that the optimal constant model, so just the one constant prediction in a theoretical sense, depending on a certain distribution, would be the median of that distribution. So unconditionally, it would be the median of the distribution, and that's exactly the value where 50% of the probability mass is on the left-hand side and 50% probability is on the right-hand side. So I guess you will know what the median is. There is again an empirical version of this thing, which is now the median of the data, of the labels you have seen, of the label vector. The derivations are slightly harder for this. They are not impossible, because I wanted to show this to you. So you have complete proofs available. It's just super annoying to read this out as a video. They are available as a deep dive as usual on the website. You can take a look at this. I actually even did the proof twice, which I guess you might have even to do here in this case. So I did this for the theoretical part and the empirical part. And then of course the risk minimizer conditionally is again then the conditional median. So that pretty much follows directly from that, because at every point x we have to solve the same problem pointwise. You get this kind of optimal conditional M estimator at every point x. So know that the optimal risk minimizer under L1 loss is the conditional median and not the conditional mean as for L2 loss. So this wraps things up here. I hope you enjoyed this session. I hope you learned something. See you later in another chapter or session. Bye bye.